Hello, everyone. Welcome to our fifth lecture. Um, so I think the the week or the week before Christmas we had our um our fourth lecture where I think primarily the focus was on the analysis of a section. All right. So with that, we were looking more at rectangular sections. Okay. And with the rectangular sections, we focused on the singly reinforced sections. Okay. So typically we have um, the cross section of a rectangular section, and then the main longitudinal reinforcement are found in the tension zone. So assuming that, so here is a tension zone. Okay, all right. Um, so we came up with a set of equations which were or which are useful to us. All right. One of the key equations was to be able to determine what's the name, um, determine a k value which we defined what k was, and also so basically if this is your and let me see if I can put this together here so that if this is the cross section and this is your neutral axis, then if you're looking at the equivalent rectangular stress block, then this is how it looks like. All right. So here will be the force in the rebar, and also we have the forces in the concrete or the compression strength or the compression force in the concrete. And then the lever arm between the two here becomes your Z. All right. And then we mentioned that the FCC and the FST will form a couple, a moment couple. All right. And we were able to define what the FCC is and also what the FZZ is. I'm sorry, the FST, and also what the Z value is. All right. Um, from the center of the rebar in the tension zone to the top compression member of the on the top compression component is the D, all right, which we call the effective depth. Okay, so we mentioned that to find the Z, which is the lever arm, then it has to be the effective depth times 0.5 um, plus square root of 0.5 plus, sorry, I think it's minus rather, minus k over 0.9. Now let's define k as well. All right. So I think we solved a few examples. I can't quite remember what the examples were, but we did solve some examples, which trying to recollect what examples this would be. Um, just trying to figure out a second. So um we can determine k where k is the ultimate moment, mu, divided by b, which is the width of the cross section, and we know our BD squared, and FCU is the ultimate compressive strength of concrete. All right, and then the MU would come from your maximum design moment, right, based on the loads that we have on the structure. Okay, so once we find Z and we find K, then we can find our area of reinforcement. So where AS, which is the area of reinforcement, will then be equal to the the maximum applied moment, M ultimate or M, divided by 0.87 FYZ. Okay, so so this is for finding the tension reinforcement. So this is like the steps required to determine the reinforcement in the what's the name within the rectangular beam. The other thing that I think we mentioned was the value of K. All right. Um, we can have a singly reinforced member when K does not exceed 0.156. All right. So if K is not more than 0.156, then we have a singly reinforced um, section. Okay. So take a note. All right. Where our M is less than the MU. All right. And then hopefully let me okay, instead of making this one MU, let me make it M so that it ties in with that of the M. So here the M is the design moment. Okay. So this will come from our design ultimate moment, and this will come from the loads. Okay, so if it's a UDL on a simply supported beam, then the maximum bending moment will become the M. Right, so that let me just put it in there for now. So these are the steps that we follow to determine our area of reinforcement. Okay, so that when you get your area of reinforcement, um, alpha, sorry, AS, which is the area of to bracket tension reinforcement. Okay, so once you find that area, your next step would be to um, pick a size or select a diameter, or select a suitable um, rebar diameter. Okay. Then once you select that suitable rebar diameter, we find the area, uh, the area of one rebar, and then we divide AS by that area to give us the number of rebar required. So what's wrong with my pen? Okay. Mhm. All right. So basically, these are the steps that we are looking at. All right. Um, okay. So with our design principle, so largely with the design principle we're working with, principle, let me see. Um, so so with a design, and put here just something small, design principle. Okay. One of the things we look at is that the failure that should occur in the reinforced concrete, especially with a beam, is that the failure should be the gradual uh, yielding of the rebar. Okay. Let's say the tension steel. This is very important. All right. If you design a beam or a reinforced concrete beam whereby the yielding is being uh, dominated by the the compression or the crushing of the or the compression zone, what is going to happen is that there will be what's the name? The compression failure typically sudden catastrophic failure. All right. So it means that you'll just be there and then suddenly you see the crashing of the concrete, which then becomes disadvantageous or in the sense that it doesn't give occupants or engineers ample time to um, prevent loss of lives and loss of property and then have some mitigation measures. All right. So let's take a note of that. Um, so failure should be the gradual yield on the steel and not um, by a sudden um, catastrophic um, compression failure. So this should be of the concrete. Okay. Um, so usually when the concrete is yielding, or when the reinforced concrete is yielding by a tension reinforcement, um, so let me put here yielding, yielding of the steel reinforcement. Uh, helps us or it enables what we call the formation of plastic hinges. Um, okay, I'll explain what that is shortly. Formation of plastic hinges. Uh, and when we have plastic hinges forming, there are a few things that occur. It helps us to redistribute the moment. Okay, so there is a redistribution of moments. We'll look at what that means. Redistribution of moments. Or typically moments can be redistributed, all right? And also this will also result in a safer and then more economical structure. Okay. Uh, so let's look at what the plastic hinges are, just explain the concept of plastic hinges. To get a new battery. So let's use with my pen. Let's explain what plastic hinges are all about. Okay. Before that, let's look at a typical cross section. All right. How yielding occurs in the structure. We usually, if this is your um if this is your stress strain diagram for a typical structure, normally this is how the shape looks like. Okay. So this is what we have for our what's the name for our stress strain diagram. All right. So normally, if this is your yield points, assuming it is like for the elastic analysis, we pretty much focus on the side. All right. The fact that we are using this because normally we look at the upper. So this is the upper. So this point is B, A, B, C. Maybe this is D and this is E. So yeah, the B and C are our yield points. Okay. So we choose the lower of the two, which is the lower yield point. All right. So basically, when you are dealing with elastic region, our focus is just on this. So this is the elastic analysis. All right. So this is what happens if you have the cross section of a beam or a structure, and then you keep applying some loads to it, you would realize that let me see if I have a do I have a ruler somewhere? Okay, that's maybe that should help me to do what I want to do. Okay, this will not be the best thing to draw. Short dash line should be fine. Okay, okay. So if you're looking at the in terms of the stresses, we have the first case where uh, at this point, if the moment applied, if the moment applied, so if the moment applied is less than the yield moment, it means that the stresses we are going to see on the beam or on the structure will be less than the yield stress. So typically will be somewhere in this zone, will be somewhere in this zone whereby the moment applied is less than the yield moment. And so you are within the elastic range. As we keep on increasing the moment or we keep on increasing the load, all right, um, at some point, the increase then will cause our structure to yield, or at least one of the fibers would have yielded, whereby now our moment is equal to the yield moment. So there will be a yielding of typically the outermost fiber of the structure. All right. So at that point, we say we have reached the yield strength. All right. So most designs are based on that fact that an increase in the load. So if let's say it's a simply supported beam, okay, a simply supported beam with some load P acting on it. So you can increase P, you can keep on increasing P from 0 all the way to a value Py, where Py is a yield load. So that yield load will cause a yield moment, and that would be what would develop into the yield stress. All right. But then if you come back to the structure here, you would realize that even though there's yielding in this zone, all right, or we have the elastic region, there's also an extra zone all the way which has not been taken into account. Okay, so this is the plastic. Uh, that is a plastic zone which still has some capacity in terms of how the analysis, in terms of receiving more moments. All right, so that can be shown over here. So again, when we begin to increase the load beyond the yield load, we would end up with a situation like this. So it keeps on. So now the yielding doesn't increase, but what happens is that the other fibers begin to yield as well. All right. So this is how it would look like. All right. So here your stress is still equal to the yield stress. All right. But now your moment has gone beyond the yield moment. Okay. So it's again, we can continue to increase our load and effectively also increase the moment to the point whereby all the fibers have yielded. This looks bad. Whereby all the fibers have yielded. Okay. So once that happens, then we see that our moment has reached what you call the plastic moment. Okay. So when the plastic moment is formed, or when we reach the plastic moment, um, at the point where we've reached the plastic moment, that section would experience what we call plastic hinges. All right, so an internal hinge is formed at that point. Okay. Um, so typically we define a plastic hinge. Um, so it is a section along the length of the beam or the member, so at which all the fibers um, have yielded. So at that point, okay. So some others can define it. The long-term definition is that it is a section at which all the fibers have yielded, such that at that point there's no further load rotation taking place without resisting an additional moment. Okay. So once this point yields, you can that section. So let's say maybe the section at where the load is applied, P, all the fibers at that particular cross section have yielded. So it is likely that you will have a plastic hinge, which is typical an internal hinge forming at that particular section. All right. So when a plastic hinge forms, then we state that a mechanism has been formed. All right. So I'm just going to use an example to explain the concepts, and then we would appreciate what goes into it. Okay. Um, so we know that if you have, and again, we prefer to use continuous beams because they are likely to develop plastic hinges and then develop some mechanism and not cause collapse of the structure. All right. For example, if you take a simply supported beam, okay, and then it develops an internal hinge. Once this internal hinge is developed, it makes this whole system unstable, okay, which means that failure is going to occur. All right. Unstable in the sense that your number of equations is now 3 plus 1, and then the number of unknown reactions is still 3. And once equations are more than unknown reactions, that creates an unstable system. Okay. So that's the idea behind it. Okay. In a continuous structure, let's say a fixed beam, all right. Um, for a fixed beam of this sort with some loading on it. Okay. Our bending moment diagram normally has the shape. Um, so it has these shapes. Let me hide the ruler. All right. So what it means is that the bending moment diagram looks like this. Okay. We should have seen it before. Okay. So I think this end will be WL squared over 24, and this will be WL squared over 12. This will be WL squared over 12 again. So these are the moment diagrams. All right. What happens is that at so this is from a load W. All right. And at this point, the likelihood of yielding occurring is high. So what we do um, is that even though the members would have yielded all right, they still have the capacity to still what's the name, receive more loads. All right. And then we would realize that, for example, if we take the ends, all right, these ends over here, we can end up with 3 hinges being formed. All right. So we can have or 3 plastic hinges being formed. We have one at the support, the other at the second support, and a third one in the middle. All right. That is adequate enough for you to still have a mechanism, or what you call so a plastic hinge mechanism without leading to the collapse of the structure. All right. So this load W, so let me give it maybe some labeling. Maybe let me call it WY, WY, WY. So WY can lead to the yielding of the material, but not necessarily to the collapse of the material, which means that there is still room for us to add more loads to the structure. All right. So we can add some loads, or there's a load which you call the collapse load. Collapse load. Okay. Which typically is more than the yield load WY. All right. And is a collapse load, which then would give us, what's the name? Um, our plastic moment. All right. Or the general idea is that we would need to add more loads to be able to define the, what's the name? Let me put it this way. To be able to, let me use the right term. Um, okay, second. All right, so let's look at maybe if I use values, maybe I can explain it for us to understand what is going on. So let's say I have um okay, so I have let me use black. Okay, so the same approach, but I'm changing the information slightly. So this is P acting on the structure. Okay. So here we typically know that the bending moment, and let me just draw the bending moment diagram. Bending moment diagram has the shape. So this is A, this is B. Our bending moment diagram looks like that. So maybe this is moment at C, moment at A. All right. So let's say the length of the entire beam is 2 meters. Okay. The moment at yield, it's maybe 12 kilonewton meters. And then the plastic moment is 15 kilonewton meter. There are ways to calculate for these. We're not looking at that right now, but uh, maybe I can get you guys a document on it just to show you how to calculate for the yield moment and then the plastic moment. Or you should have done something similar in strength of materials, anyways. Okay. So let's say our MA, if you do the computation, our MA will be equal to, I think it's 3PL over 16, and then MC will be equal to 5P times L over 32. Okay, so these are the equations for the moments. All right. So let's say P is 25. So we're just assuming, let's say P equals 25 kilonewtons. Okay. So once P is 25, what will be our MA? Our MA will be 3 times 25 times 2 over 16, and that would give us 9.4 kilonewton meter. Our MC would also follow a similar format, and that will be 7.8 kilonewton meter. Okay. Now, if you look at them, both these values are less than the MY. All right, so they are less than MY. And what this simply means that, so let me just put that into writing. So both moments are less than the yield moment. All right, that's something. So because they are less than the yield moment, it means that the beam is safe, right? Because it's not yielded, so the beam is safe under the working conditions. And let's move further where we increase P. So let's say let P be equal to 32 kilonewtons. So if P is 32, it means that our MA will be what? 3 times 32 times 2 over 16. And that will give us 12 kilonewton meter. Okay. And then our MC will be 10 kilonewton meter. Okay. So again, our MC is still less than MY, but then our MA is now equal to MY. So what it means is that the section at A has yielded, whilst the section at C is yet to yield. All right, so the cross section at location A has reached its yield limit. Let me say cross section at A has reached um, its yield limit. Okay. So what it simply means that at least one of the extreme fibers and that cross section has reached the yield point. All right. So normally in elastic analysis, this will be the maximum allowable load that we can put on the structure. All right. So we normally, if you're doing elastic analysis, you cannot have a load more than 32 kilonewtons, right? Because at least one of the sections has yielded, right? But let's push things a bit further just to explain the concept of plastic hinges forming and that kind of stuff. So let's P be equal to 40. So if P is 40, our MA will be 3 times 40 times 2 over 16. And that would give us, do the computation, and that will give us 15 kilonewton meter. All right. Our MC, the same thing, will be equal to 12.5 kilonewton meter. So in the case of MA, it is equal to the plastic moment. Okay. While this one is more than the yield moment, but is less than the plastic moment. Okay. So because there's plastic moment at A, so at location A, what it simply means that all the fibers at A have yielded or have reached their yield point. Okay. So because of that, it means that a plastic hinge will form at location A. Okay. So typically, if I'm to draw the cross section at A, this is how the cross section at A would look like. Okay, so this is at A. And then at C, that's how the cross section at C would look like. So this is at C. So at A, all the fibers have yielded, and at C, certain part or some part of the fibers have yielded. All right. So going back, what it simply means is that if I draw my cross section, my structure again, sorry, it means that I would have a plastic hinge, a hinge forming at this point with a load P, where RP in this case is 40 kilonewtons. All right, for this particular case. So this is A, C, and B. All right. So what it means that if you have your bending moment diagram, so the moment at A is equal to your MP. Okay. Now, what this means is that because a plastic hinge is formed at A, there would be it means that at A you cannot A cannot resist any moment, any additional moment, right? Beyond a load of 40 or a moment of 15 kilonewton meter, if let's say we increase the load to 45, all right. So 45 means that an additional load of 5 have been added, right, from the 40 to the 45. This additional load cannot be resisted by, cannot be resisted uh, by location A. All right. So what this means is that this additional load or the moment coming from this additional load needs to be redistributed. So moment from delta P need to be redistributed. Okay. So into bracket, we are looking at moment redistribution. Okay. So basically moment redistribution. So this additional load, all right, because a hinge has been formed at A will behave as though it is a hinge, right? So this additional load P, which is 5 kilonewtons, will lead to what's the name? Moment forming. So it means that will end up with a bending moment diagram looking uh, like that. So this becomes our bending moment. Now this is the positive, sorry, and this is positive, and this is negative. It's positive. So this becomes PL over 4, where our P or our delta P here is the 4. So it becomes 4 times 2 over 4. Am I, sorry, it's 5, not 4. P is 5. So 5 times 2 over 4. This will give me 2.5 kilonewton meter. All right. So it means that this additional load will then be taken over by, let's say, the moment at C. All right. So it means that now the moment at C, so in this case, when we increase P to 45, all right, what it simply means is that the moment at A will still remain at 15 kilonewton meter. It cannot increase beyond the plastic moment. But then MC can increase, all right? Where MC would increase from initially at 40, MC was 12.5. So 12.5 plus 2.5, and that'll give us 15. Okay. And this 15 is the highest MC can be. MC cannot be more than the plastic moment. All right. Which means that a load of 45 kilonewtons is the highest load we can put on the entire structure. Any increase in the load, let me see if I'm still recording. Okay. Any increase in load, let's say, if we let P be more than 45, that will lead to the collapse of the structure. Okay. So let's take a note of that. Okay. So pretty much P of 45 kilonewtons can then be termed as the collapse load, right? And this is what we need to understand, all right? So between the yielding, where yielding occurred at 32 kilonewtons to where we reach P of 45, which is the collapse load, it means that between, I think, from 32 to 45, we have added from 32 to 45, we have added what? An additional 8 kilonewton load, which is approximately about 40%, yeah, of the 32. kilonewton. So it means that beyond the elastic limit, the additional load, or we have about 40% additional load, which can be added to the structure before collapse occurs. Okay. Why are we going through all these things? Why are we going through all these plastic loads and plastic hinges and all of that? We, in design of concrete members, we take into consideration moment redistribution. Is very important to us. All right. The reason why our structures do not collapse right away when some part of it reach like where some sections of the structure have experienced yielding of all the fibers is because we take into consideration um, 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 redistribution of moment. All right. So that if certain parts of the structure cannot take additional moment, there are some parts which still have enough room to take these additional moments without leading to the collapse of the structure. Okay. And this is very important in reinforced concrete design and even with other, what's the name? Other structures, I mean, other materials. All right. So going back to where we were, one of the things is that so I mentioned that when it comes to yielding of the or when it comes to reinforced concrete, would prefer or designing reinforced concrete member. It is advised that the failure should rather be the yielding of the steel member and not the crushing of the concrete. All right. Because when the steel member yields, plastic hinges are formed, and thereby we can redistribute moment. Okay. And that will lead to a more safe and economical structure. So for us to be certain, so to be certain of yielding of what's the name of the tensions to you, the code gives a limitation on what the depth of the neutral axis can be. All right. So if this is um if this is your section, and then we have here this the equivalent rectangular stress block. Here is our x, okay, the depth of the neutral axis. Okay, so you are saying that this depth x um has to be within a certain range so that we can ensure that our tension steel will be yielding all the time and not the failure, I mean, the compression failure of the concrete. All right. So this X should not exceed some parameters. We'll define them very soon. BP minus 0.4 times D. Okay. We already know what D is. D is from the centroid of the, the area of steel in the tension zone to the top compression portion. All right. So our X should not exceed these values. Okay. If you want to maintain failure of the tension steel. All right. So this BP here is defined as the moment um, at the section after redistribution, and then the moment at that same section before redistribution. Re before redistribution. Um, what's happening? Distribution. Um, so what it simply means is that the moment redistribution here, um, so normally, again, if you remember, the code also specifies that our depth of the neutral axis should not be more than 0.5 d. I think we discussed that in our previous uh, calculations, all right? To ensure that, what's the name? Tensile yielding um, of steel, all right? So to ensure that our x should not be more than the 0.5 d, which means that if we compare equation 1 and compare equation 2 together, we would realize that our BP can be more than 0.9. So the lowest value of BP um, is 0.9. All right. So the 0.9 here also indicates that our moment redistribution, uh, moment redistribution should not uh, exceed 10%. Okay. All right. So because sometimes when you are redistributing moments, what happens is that um the let me go back to what I have over here. Sometimes we are redistributing moments. What we need to take into consideration, sometimes some of the let me put the words right. When redistributing moments, um how do I explain this? I'm trying to get the right words to explain. Um okay, when redistributing moments, certain moments um should not be reduced uh, by more than 10%. All right. So reduction by 10%. So it should not be more than 10%. All right. For all of these parameters to make sense, the moments redistribution should not exceed 10%. All right. So you cannot take more than 10% of uh, moment from one end and then share it amongst the rest. That's like the basic explanation of what this means. Okay. Um, all right. Would this will come into full circle going forward? The reason why we are going through all of this is because we need to understand that in design, moments are redistributed. All right. And typically we use uh, a factor of 0.9. If one use a different factor, there are other approaches we can go with, but the code typically specifies a 0.9 or a 10% non-exceedance value. Okay. So some books will define the BP or beta subscript B as a ratio of design moment to the ratio of the maximum elastic moment. Okay, it's the same thing, right? So going back, um, where we have the case whereby, so let me take you up all the way. Hopefully my screen doesn't freeze. Yeah. So here, this So here, your K is less than 0.156. All right. So what happens if K is more than 0.156? What happens to our structure? All right. And this is something that it does occur plentiful times. All right. So typically you would realize that let me put a nice subtopic over here. Um, so let's say rectangular section. And alien geometry, rectangular, rectangular section. Um, with compression um, reinforcement. Okay, reinforce. Um, okay, so here, how do we arrive at that? Okay. A few things to note. Um, if m is less than 0.156, what's FCU BD squared, then we use singly reinforced, okay, as we've done previously. Okay. But what if your moment is more than 0.15 FCU BD squared? Okay. So let's say, or if K is more than 0.156, right? This also means that the same as K being more than 0.156, or K is equal to at least equal to 0.156. So here, it means that we'll need to have, so some will say this is called doubly reinforced. Okay, some books use that. Doubly reinforced. Okay, it means that the concrete in the compression zone is not adequate to resist the the moment. All right. So when this happens, what this means is that so we consider the ultimate moment. Ultimate moment exceeds uh so let's see the moment resistance, yeah, of the concrete. Okay. So therefore we need reinforcement in the compression zone. Okay. So with that in mind, I can quickly draw that right here. Okay. So this will be my neutralizers. So we have our rebar in our tension zone. So that'll give us AS. We know that already. And then Now we need a new set of rebar in the compression zone. So we call that AS prime. Okay. From the centroid of the um, steel in the tension zone to compression flange is called D, which is the effective depth. We can do something similar to, and this is the effective depth for the compression called D prime. Okay. So we have these parameters. So we can also draw the what's the name? We can draw the axial, sorry, the strains. So the strains will look this way. Um, so these are the strains. So here will be your sigma, sorry, your epsilon. Uh, this will be your epsilon CC, and right here will be your epsilon SC. So still in the compression zone, this will be your epsilon ST. All right. So the strains in there. Now, if you look at the equivalent rectangular stress block, you have um, we have something like this. Okay, so this is equivalent rectangular stress block. Okay, so mm, I'm careful to show that this is actually, so here we have, so this is our FST. Would also have in here um, F, so this will be our FSC, and then this becomes our, so let me change the colors. Um, oops, this is taking forever to delete. I think I'm using the wrong eraser. Okay, great. So here I have my FSC. Then I also have my FCC. All right. So these are the forces within the cross section due to these extra reinforcement in the compression zone. All right. So here comes my Z, which we know what is the lever arm, and then what again. So um this distance here is our S, where S is 0.9 x, right? We've already defined that. And then so this is our x, okay. And then x cannot exceed d over 2. All right. So this is a neutral axis, all right, where x cannot exceed d over 2. So let's put that over here. Then, all right. So again, take a note, x cannot exceed 0.5 d over 2. It's the same thing. Okay. So here we know that our mu 0.156 FCU BD squared. So we are going about this approach because the moment applied is more than mu. All right, that's the idea. Right. If the moment is less than mu, then it's singly reinforced. All right, that's the idea. So let's see how we can develop equations for these, and then how we can implement or use these equations. Okay. So if you are summing forces, so let's say summation of forces, it implies that my FST will be equal to FCC plus FSC, right? Where the FCC is the fourth. Let me just put them over here. FCC is concrete compression force. Okay. then FSC, um, yeah, maybe still in compression. All right, or still in the compression zone. Then the FST is still in tension force. All right, these are like the definitions. Okay, so let's look at the FST, like the how we can find FST. We have that already. We know that FST is equal to 0.87 times the yield strength times the area of steel. All right, this has already been formulated. And what it means that our FSC would also be something very similar, 0.87 Fy times AS prime, where AS prime is the area of steel in the compression zone. All right, so AS prime is area of steel in the compression zone. And let's find FCC. FCC, again, that has already been done before. It becomes 0.45 F sub Cu BS, where S is the height of the compression zone. All right, that's the stress block for the compression zone. So let's say we can rewrite all of these nicely. So it becomes 0.87 oops, FYAS being equal to 0.45 F sub Cu BS plus 0.87 Fy AS prime. All right, straightforward. If you want to simplify it, we know what S is, so we can, if you want to sub this and put in D instead of S, we know that S is 0.9x, which is going to be equal to 0.9 D over 2. So this becomes 0.45 D. So wherever we see S, we can put 0.4 and 0.45 D, which means that our equation then becomes 0.87 Fya sub S will be equal to 0.201 FCU-BD plus 0.87 FY-AS prime. Okay, so that's just for the summation of the forces. Now let's look at moments. All right, so let's take moments. Take moment about the centroid, for example. Okay, so about the centroid of the tension steel. All right, about the centroid. AS prime. All right, so if we are to do that, then it means that the moment M will be equal to, let's go back here, so it becomes FST times Z. That one is oh, sorry, about the tension steel, so not the compression, sorry. Okay. So AS, not AS prime. All right. So then it becomes FCC times Z. All right. So we're taking a moment about this point right here. So FCC times Z, and then this distance here, all right, is going to be simply D minus D prime. All right. So here is D minus D prime. All right. For that distance, so it becomes plus FSC D minus D prime. Okay. That's it. So we can put whatever we had previously in there. Initially, this is our FCC, so that becomes 0.201 FCU times Z. Okay, so now let's go and look for Z somewhere. Let's just find Z again, or let's find Z in terms of D. All right. So we I think we've done this already, but let me just put it into the box form so that we appreciate it. Previously we know that or we can find that Z is equal to D minus X over 2. So going back over here, the lever arm Z will simply be D minus S over 2. It's because FCC is acting right at the center of the so this distance here, let me just put this distance here is S over 2. It's gonna make it look funny. Okay, so let me just rewrite it nicely. Too far. So this distance here, what color would work? What color would work? Okay, let me just go with the red. So this distance here, okay, is S over 2. Just take note. So Z is D minus S over 2. So this will be equal to D minus S the same as 0.9x. All right, over 2. All right. And then what do we have here? And again, Z is equal to D minus 0.9 over 2 into bracket uh, D over 2, because D over 2 is what? I think we have that sum over here. D over 2 is equal to X. I mean, that's what we are basing all our calculations on. So in that case, our Z here will be equal to 0.775D. Great. Okay. So I can come back into this bit and then instead of writing Z, I can put 0.775D. All right. Then plus 0.87 Fy AS prime. Then we have D minus D prime. All right. So this is equal to our moment M. So simplifying this, we get 0.156 FCU BD squared. This has been done somewhere in our last lecture. So I'm just in the end, this is what it looks like. Uh, so just repeating stuff. D minus D prime. Okay, great. So here, if I'm to make A as the subject, so let's see, making AS prime, sorry, the subject. It means that if we rearrange everything over here, our AS prime will be equal to M minus 0.156 FCU BD squared all over 0.87 FYA. No, sorry, no more A here because we've made that one the subject. So, okay, FY. So, FY D minus D prime. Okay. So, this is what we use to find AS prime. Okay. Some documents would also have it in this form. K minus K prime. All right. Into brackets FCU BD squared over 0.87 uh, y d D minus D prime. What just happened to my screen? Just make sure everything is still recorded, otherwise it will be annoying. Okay, great. So, right. So once we have that, so here, let the K prime be equal to 0.156. All right. Let me. All right. So here the K prime, as I mentioned here, is 0.156. All right. And we know how to find the K, where K is equal to the design moments divided by the FCUBD squared. Okay. All right. So I'll just recopy this equation that we had earlier for the um, summation of the forces in this section. Okay. So let's multiply both sides. Let's say we multiply push when it's moving. Okay, so multiply both sides uh, by 1 over, let me hide this guy. Okay. By 1 over 0.87. Can just rewrite this nicely. So 1 over 0.87 Fy. Okay. So once we do that, we'll end up with so it becomes AS will be equal to oh, I think I took something out. What's wrong with my pencil again? Oops, okay. You're kidding me. Something is not right. All right, so let's wrap this section. So once we do that, it becomes AS being equal to 0.21 FCU PD divided by 0.87 Fy plus AS prime. I think this is some FCU over here. I think so. Okay. All right. So that let's see. We also know that or we do know that Z is equal to 0.775D. All right. The idea is that we're just trying to formulate an equation that is easier to work with. All right. So I can do another set of uh, math movements, as we call them, and then just get what we want, all right, through that, okay? So here, I can multiply both sides by Z. Okay, it doesn't change anything. But what I'm going to do is that the top Z, I'll convert that into 0.775D. All right. So that it means that my AS now will be equal to 0.201 FCU BD to bracket 0.775D all over 0.87 FYZ or DZ. Sorry, FYZ, there's no D, plus AS prime. So our AS then would be equal to 0.156 FCUBD squared over 0.87 F sub YZ plus AS prime. Okay, so this is the equation. So this equation will find or will give us the area of tension reinforcement. And then the one we had earlier, which was this here, the AS prime here. This will give us the area of compression reinforcement. So that is it. So now to find Z, which is what we need here, Z then would be, we know we have the equation D, bracket open 0.5 plus square root of 0.25 minus K prime over 0.9. So D would always be a constant value, where our K prime here is 0.156, right? So I think with this we can look at some examples and then see how this entire set of equations are used for the design of bending members. All right. So before we before we look at the example, let me just add one little details that will be of use to us going forward, which has to do with some limitations that the code puts on us on to ensure that the tension steel and then the compression steel have yielded, and not rather the crashing of the concrete being the failure mode. Okay. So let's see. So I think we've gone through this. Where's the stress block? Yeah. So we've gone through the stress block. We have seen the strain block also. So I'm just going to pop that here quickly. Okay, so this is the strain. And then so this is our concrete compressive strain. Then we also have here the strain for the concrete in compression. Okay. Then the line here will be our neutral axis. Okay, so let's have that. So this height here is supposed to be the X, and then from the compression rebar to the neutral axis is X minus D prime. Okay. So with this, we could write using the principle of similar triangles, write an set of equations that can be used to arrive at that limiting value. All right. So here, epsilon SC divided by X minus D prime will be equal to that of the concrete divided by X. All right. So at this point, we know that the strain at concrete at the ultimate strain is given, I think, by 0.03 5. So we can put that in there. So let me just write that in the space. So that would be so I'm just going to rewrite the whole equation here. So 0.0035 divided by x. All right. So here, again, we can expand. When we expand this equation, we'll end up with, so let's say x, let me do it this way, x minus d prime over x will be equal to epsilon sc over 0.035. Okay. So the left side could be rewritten in this form, d prime over x. So then it's the same on the right-hand side. Okay. So here it means that d prime divided by x would be equal to let me get this right. So it becomes 1 minus epsilon sc over 0.035. Okay. So this is an important equation here. It guides us as to what the limiting factor will be in terms of the prime over x, where the prime is supposed to be the effective depth for the compression rebar. Okay. So in that case, for example, let's say, let me put that in the space right here. For example, if you're looking at high yield where the yield strength is 460 newtons per millimeter squared, um, what this means is that um, its strain at yield would also be 0.02, which in this case is the same as the epsilon SC. So we can put that into this equation and let's see what we'll get. Okay. So it becomes d prime over x will be equal to 1 minus 0.002 over 0.0035. And this will give us 0.43. Okay. So what this means is that for we to have yielding, yielding of the compression steel, we cannot have the prime over x exceeding 0.43. Okay. And this is quite important to us. The other way to look at it is if, for example, we have also established that x is equal to 0.5d. So wherever I see x, I can put in 0.5d. And I would also realize that that means that d prime over d should also not exceed 0.215. And this is important to us. All right, so let's take note of these two limiting factors. All right. So the moment any of these values, for example, if you find d prime over x and it exceeds 0.43, it means that there will be crashing of the concrete or failure of the reinforced concrete beam would be dominated by the compressive crashing of the concrete. And we don't want that because this type of failure is sudden and catastrophic, right? So we want to stay away from it. Okay. All right, so let's look at the example. So let me see example 1. So for an example, let's say we have a beam which has let's say some bars. We don't know how many there are. I'm just showing two of those, but we don't really know how many bars how many rebars that we need with respect to the cross section. All right, so in the compression zone, we have AS prime. In the tension zone, we have AS. We are told that the effective depth D, so D is equal to 440 millimeters. Okay. Oops. All right. Uh, what is happening? All right. Everything. Okay, great. Then the effective depth for the compression zone D prime, that's given us 50 millimeters. Okay. So let me just go back and write this to be AS prime. Okay. And so let me just put in some writing. The section shown, um, is to resist an ultimate design moment. um, let's say of 235 kilonewton meter, right? So we have to determine the reinforcement required. Okay, so that's the question. Determine the reinforcement. Okay, great. So let's put a few things together. The FCU of this concrete, which is the compressive strength, is 30 newtons per millimeter squared. Then the yield strength of the rebar is 460 newtons per millimeter squared. You pick some books and they write it in as MPa. That's the same thing. All right. So what do we do? Let's first figure out if we will need whether it's a singly reinforced system or a doubly reinforced system. And the deciding factor will be the value of K. All right. So solution. So let's find K, where K is equal to, oops, K is equal to M over BD squared FCU. Okay. And please take note of the units. They're very important. Everything should be in the same unit. So here we have 285. So I'm converting everything into Newton. So let me just I'll put a unit in a separate set of colors. Um, the width, sorry, so the width of the beam is let's say 260 millimeters. So this is the B. So I have 260 times a D of 440 squared, then an FCU of 30. Okay. So if you compute all of that, we should have 0.189. So let me write the units by them. So this is going to be Newton millimeter. This is in millimeter. This is also in millimeter squared because of and this is also in Newton per millimeter squared. So we'll end up with a factor without any units, all right? Now we need to compare this K to the K prime, all right? We earlier mentioned that K prime is 0.156, okay? So here our K is more than K prime. So because K is more than K prime, we need compression reinforcement, okay? So we need compression reinforcement. Okay. So basically, we are looking at a doubly reinforced system. Okay, so that's the idea. So one case more than that. Um, one so let's make use of the things I put in this table earlier. So let's make use of these information over here. Let's just make use of it. Just to just to confirm that the compression steel would yield. All right. So let's say D prime over D. Okay. So this is 50 over 450. Okay. And when we went 440, sorry, when you compare this is 0.11 and 0.11 is less than 0.215 as we had earlier. All right. So it means that with these, um, what's the name? The compression still would have or will have yielded. Okay. Which is what we need. All right. So great. So everything is working over here. So now let's look for AS prime. Let's find the compression steel. All right. So here we want to find the compression steel. So AS prime. The equation for AS prime, we found it earlier that it's K minus K prime. FCU BD squared over 0.87 FY D minus D prime. All right. So this is going to be our K is 0.189. Our K prime, it's always going to be 0.156. Okay. At least with what we've been doing so far. And then our FCU is 30, our B is 260, and our D is 440. Okay, so all squared. Then we divide this by 0.87. Our FY is 460, which is the yield strength of high yield steel. All right. Then this is times a D of 440 minus 50. Okay. So this will give me an area of 319 millimeters squared. Okay. So here is the area of steel we need for the compression section. Okay, so that's for the compression steel. Okay. Now let's do that for the tension. Okay, so for the tension steel, that is AS prime. So that's AS, sorry. So the AS would be a pretty long equation. I think we had that written somewhere earlier. Um, so this will be equal to K prime FCU BD squared over 0.87 FY Z plus AS prime. All right. So again, this is going to be 0.156 times 30 times 260 times 440 squared divided by 0.87. Our FY is 440, sorry, 460. So it's 460. And here, take note, Z is 0.775D. Okay, we have already established that. So Z, for this case, Z is 0.775D. If it were singly reinforced, the value of Z would vary. All right. So here it becomes 0.77 times a D of 440. Sorry, 440. Let me just clean this. Okay. And then plus the S, which is the 319. Okay. So if you compute all of this, you would end up with uh, an area of 245 millimeter squared. So then this becomes the area of seal required for the tension zone. All right. That's in its simplest form what these um, 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 method or what these sets of equations are used for. All right. Um, there are quite a number of examples out there. I'll try and see if I could put some together for you guys to have a look at. But in the simplest terms, these are how we use the equations. Okay. So from here, if you have okay, just give me a second. I want to drag some few things. Okay, let me see. Okay, great. All right. So this there are some examples. As I said, I'll look for a few and then put them together for you guys to have them. All right. So just some summary on the side. It's always good to have some form of summary. It's always go to. All right. So let me put that into this box. Um, Wait. So if you're looking at a case where you have only tension, when you have only tension or where the tension still is yielding, it says that our X over D should not exceed 0.636. And then for compression, so for the compression steel to yield uh, too many um, the D prime over X should not exceed 0.43. Or as we had it earlier, or D prime over D should not exceed 0.215. All right. And they are very important to us. All right. And these are the guiding principles that the design code BS8110 is based on. Okay. Now let's look at some other cases where um, usually we have this system in place. With reinforced concrete, normally when we are casting concrete, if I'm sure most of us have been to site to see what concrete casting is all about. And usually when you are casting concrete, there are a few things that happen. Um, so generally, the beams and slabs are cast together, right? The beams are cast together, or they are cast what you call monolithically. All right. It means that they are cast as though they are one entity. Okay. Um, so usually when that happens, we can take advantage of that situation whereby both the beam and then the slab are behaving as though they are one. All right. So we could add the part of the slab or some part of the slab to the beam. All right. And then by doing so, we are increasing the amount of concrete in the compression zone. All right. What we've been doing so far has been rectangular beams. Okay. In reality, we don't, or hardly do you see any project whereby only beams are cast. Normally, you see that beams are cast with slabs. So if it is a building, if it's a theater, if it is a church auditorium, you still end up with slabs and beams being cast together most of the time, right? So we take advantage of that behavior, and then we tend to normally increase the or add a portion of the slab to the beam. Okay. And then this would increase the amount of compression or to increase the compression zone or the concrete compression zone. And mostly when that happens, it means that we are likely not to need compression reinforcement. Okay. So let me put that into writing for us. So generally, the beams and slabs are cast together. Um, and then at mid-span, um, so it is more economical in such cases to design the beam as a T or what you call an L section. Or look at so in that case we try to include adjacent areas of the slab, okay, as part of the beam. Okay. So um usually we call these types of sections flanged sections. And with these flange sections, we have two types. Um, we have the T section, then we have the L section. So an example of a T section, as the name indicates, would be looking like this. Okay. So normally, the top portion here will be the slab, and then the bottom portion will be the beam. All right, but then together they act as one. So usually you find this at midspan, and then we have the L section, which can have this shape. So it's like an inverted L, right? So again, the the base here will be the beam, and then the horizontal section here would be the slab. Okay. I think I need a new screen. Mhm. Okay. So that's what we have. And let's see how all of these tie in, at least from a typical um, beam slab design, right? So if this is your, uh, let me see how good I am at drawing straight lines. So if, for example, we have a system like this, okay, let me, uh, sorry, struggling with my screen for a bit. Just not happening. Just let me just redraw. Hopefully it works this time around. Let me take off the, okay. So let's say this is what we have. All right, so this is something like that. Um, so an example would be if I take this section here, this can be basically uh, a T, whilst the section here can be an L. So this is an L and this is a T. All right, so that's basically what goes into this whole flange sections. All right. And the way we also analyze these flange sections are quite similar to that of the rectangular sections, with just some minor differences. I would explain what the differences are, and then we can move on from there. All right. Um, so normally if you take, so let me use the T section to explain the concept. So if you have a T section, so if you have a T section, all right, these are some of the key components of the T section. So this, we call it BF, and then we have here HF. This is BW, and then our HW. All right. Um, so the BF is the width of the flange. The HF is the height or the depth of flange. All right. Okay. Then the HW would be the height of the web. And then BW is the width of the web. Okay. Now, when dealing with these um when trying to what's the word? Trying to analyze a T section, we need to find the width. All right. Because here we have two width, either the width of the beam or the width of the web, and then the width of the flange, or in a way, a portion of the width of the slab and then the width of the beam. So which ones do we go with? And because the width of the slab and that of the beam act together, we need to find what we call an effective flange width. So effective flange width. Okay. To find an effective flange width, the code BS 8110 clause, I think 3.4.15 has some information as to what the effective flange or the effective flange width can be. All right. So if it's a T beam, like what we are looking at right now, so for T beams or for T sections, um, your flange, we choose the flange width should be the minimum of one of these two. Either the actual flange width or we find the width of the web plus an important factor or an important length Lx divided by 5. I will explain what Lx is shortly. And then for oops, my screen is messing up. And then for the L beam, the minimum effective length, so sorry, the minimum effective width, we choose the minimum or the lesser of these two values. Again, the actual flange width, or again BW plus L sub S over 10. Okay. So here our Lx here is defined as the distance between zero moments. Okay. And that distance between zero moments pretty much is supposed to be the distance between the spans, all right, or from the center of supports. So for example, if you have, okay, I don't need to draw, just go back and then explain over here. So if you go back here, then technically this distance here will be your Lx, or from here to here will be our Lx. Okay. So uh, so we usually take Lx to be equal to 0.7 L. Sorry, so let me go back and do this correction before so that it doesn't stay. So instead of here being Lx, rather, this is our L. Sorry. This is L, right? Not Lx. Okay, so this is L. Then the Lx will be 0.7 of this L. Okay, that's what it's usually taken as. And what this simply means is that this is supposed to be an effective length. All right. So another way to look at this is to be called an effective length. We'll look at that a bit more when we look at columns, right? the effective length is dependent on what the support conditions are. So if they are pin at the ends, we have it the effective length is L if it's pin fixed, different value if it's fixed. If it's a cantilever, the effective length would also vary. All right. So okay. Let me go ahead and put some few things together. So as I discussed earlier, the flange generally uh, provides what's the name? Large um compression what's the name area. Okay. Um so hence we and it is usually uh screen is off a little bit. Okay, so hence usually unnecessary to determine um the case. Sorry, I have to slow down a little bit. The case with compression reinforcement. Okay. So usually it means that where you have a flange, you are basically going to focus on singly reinforced. All right. So our focus will be on singly reinforced. And with a singly reinforced, there will be two options for us to look at. And these options will be based on the neutral axis. So if the stress block lies in the compression, and the second case, if the stress block lies in the or lies below, just say lies below the compression of flange. So let's look at the first case where the stress block lies in the compression flange. What this means is, so let's say case one. All right, so stress block in compression or lies in compression flange. All right. Okay. So if we are to redraw our section, let's say this is a T beam. All right. So what it means is that I think this might be too small for what I want to do. Let me see. Okay. Sometimes everything slows. Daddy, let's close you. So the flange, I think let me get this in maybe bigger a little bit. Okay. It's so that we see, uh, so in this case, we have the neutral axis. Put the neutral axis somewhere. Let me change the color. Uh, so we do have the neutral axis, and I think the pieces all over the place. And this, okay. So let's say this is our neutral axis. So it's like which means that our stress block will lie within the compression flange. All right. Um, so we end up with all right. So something like this. That if we have the rebar here, then this is our FST. So let me get a neutral axis again. Sorry, I'm having some challenges with my screen today, so it tends to act up from time to time, like right now. Okay. Yeah. So this is my FCC. We can see that it looks exactly the same as that of the rectangular block that we had. I mean the rectangular section. So when the stress block lies within the compression flange, the behavior of that flange, so whether it's a T section or an L section, its behavior is the same the same when comparing it to the rectangular stress block, right? So everything is the same. Your Z will be the same. Then here will be your S. This is your X. All right. So that this case works if your S is less than HF. So if the height of the stress block in the compression zone is less than the height of the flange, then it means that your stress block will lie within the flange, right? So under this case, your AS will still be the moment divided by 0.87 FYZ, and then all other parameters remain as they are. All right. So let me see if I can bring up an example for us to um, use that to explain what is happening. Um, so let's say we have a T section. So let's say an example. Okay. So we have a T section, and then let's put some information in terms of the um, size. So this is 800 millimeters. Um, here we have 150 millimeters, and then what else do I need? So okay, so this question, I think I just have to write a question down. So yeah, we have AS, where AS is given as 1470 millimeters squared. Okay. So the question states that we should determine the ultimate um, moment. Okay, so the ultimate moment of resistance of the T section. Um, so our Fy is 460 newtons per millimeter squared. And the FCU is 30 newtons per millimeter squared. Okay. So here, what do we do? I think the effective depth D, um, so D, the effective depth D is given to us as 420 millimeters. Okay, so let's solve this example. I might have to restart the screen. So let me solve this example and then we can move from there. All right. We know that here, there are a few things, no compression. All right. So in terms of the stress block, this is our stress block. Okay. Here's our FCC. This is our FST. Okay. And then we know that our FCC plus or FCC is equal to F. Let me just put it that way, so I don't have to bring a negative sign. I'm sorry. So this is equal to FST. All right. And then we know our FCC, we know the force within the compression, or there's a sort of axial force in the compression zone where FCC is 0.45 FCU. Um, Here will be what the BF, because it's within the flange. So the BF would be, so here the B that we'll choose is because the stress block is found within the flange, our B will be the width of the flange, all right? And then times S. So this will be equal to 0.45 times 30 for the FCU. The BF is giving us 800 millimeters. And then, okay, we don't have S, right? So now we first have to find S. Then after finding S, we can use that to find the ultimate moment. Um, so now we don't know what S is, but we can find it. Okay. So FST will be equal to 0.87 FYAS. So that will be 0.87 times FY is 460. And we're given the AS to be 1470. All right. So we can equate these together and find S. All right. So here S then will be equal to 0.87 times 460 times 147 divided by um, divided by 0.45 times 30 times 800. So this should give us an S value of 54 millimeters. Okay. So once we find S, um, our next thing will be um, to determine what the lever arm would be, the Z. Okay. Why Z? Because we want to find the ultimate moment, where the ultimate moment M is equal to FCC times Z. Okay. So we don't know the Z yet. So to find the Z, we know that Z From our first principles that is equal to d minus s over 2. All right. So that then will be equal to our d. D is 420, becomes 420 minus 54, 54 over 2. And this should be equal to 393 millimeters. Okay. So it means that our M then will be 0.45 times 30 times 800 times S of 54. Just, so then when you do the computation, it becomes 229 times 10 exponent 6 Newton millimeter, which is the same as 229 kilonewton meter. Okay. So for this problem, we were given the area of steel, we were given some other parameters, and then we were asked to determine what's the name? The ultimate moment, design moments. Okay. If you look at the value of S, right? So S here is 54 millimeters. Our HF is 150 millimeters. Okay. So because S is less than HF, it means that our neutral axis or the stress block lies within the compression flange. And that is basically what we have done with respect to the example we just looked at. Okay. Now let's look at, so this is the first case, stress block in compression flange. Now let's look at the second case. Okay. Okay. So where the stress block um it extends beyond or below the flange. Okay. So it means that our S is more than HF. Okay. That's what it means over here. So again, if we are to draw our stress block, so let's say we are still using the T flange as an example. Uh, the so we have our stress block, but in this case, then the neutral axis will lie below the flange. Okay. And when that happens, this is what we have. I think at some point I have to start this piece, restart this piece. So this is let me see if I can. I'm even careful to delete anything now because of how the piece is misbehaving. Okay. So we have a stress block 1 for the flange, and then another one for there's another one over here. Okay, so there are two. So this will be the FC. I'll call it F. So the axial compressive force for the flange. And then here, this will be for the web. And then we have that of the steel. All right. So few parameters. Let me put that in here. This whole height here is our S. This short height here is SW. So for the web. All right. And then, of course, we know we have our D and our Z. So I'll have two Z values. Okay. The first one is my Z1, and this one is my Z2. So the Z2 will be the lever arm between the FCW and then the FST, and then Z1 will be the lever arm between FCF and then FST. Okay. So let's see a few things that we know. So let me just put this over here. FCF is the force which is developed in the flange. In the flange. Okay. Then our FCW is the force which is developed in the area of the web, okay, in compression, because it's not the entire web. Some part of the web is in compression and some part is in tension. So if we look at the so this side here is a part of the web in compression. Okay. So let's take note of that. Okay. So once we have all of these, now the goal will be to find pretty much what the Z values would be. All right. So we know that the moments in the flange, so this is the moments in flange, all right. So the moments in the flange. Okay. So here MF, so here the MF, which is the moments in the flange, would be so that will come from the FCF, right? So FCF times Z1. All right. And this is the same as 0.45 FCU times the BF times the HF. All right. And then our Z1 here, if we look at Z1 carefully, Z1 will then be equal to pretty much the effective depth minus half of the height of the flange. So this distance here to the center of the area of steel, that is your D. And here we have our HF. Okay. So Z1 is simply D minus half of HF. Okay. So times D minus HF over 2. Okay. So for the S, which is the depth of the stress block, if it's equal to that of the flange with um when you do these calculations, you compare the moments with that of the one we go from the flange. All right. So that if your moment or the ultimate moment is more than the moments of the flange, it simply means that the stress block lies or the stress block extends below the flange. Okay, so when M is greater than MF, okay, this implies that um, stress block extends below the flange. So when that happens, it means that we still need to find the depth of the stress block for the web portion in the in compression. So this SW here is simply going to be S minus HF. All right. So what it simply means, if you go up here, yeah. So this height here pretty much is the HF. All right. So SW will be equal to S minus HF. All right. So this becomes a simple math problem. Um, where's my write-up? Okay, it's back. All right. And then by so doing, to find out Z2 then becomes D minus HF minus SW over 2. All right. So that if we take moment about the tension steel, that means that our M here will be FCF Z1 plus FCW Z2. All right. So there's something to take note of. Um, so we can I think this is supposed to be like the exact method to solve it. We have both the exact and then the approximate method. All right. Um, the goal is that here, um, once you find your HW, or the goal is to find XW, all right, because the when finding the moment, the Z2, the Z2 here is dependent on SW. So we first need to find SW. And once we can find SW, then we can determine the moment, and then use that information to find the area of steel that we need. All right, because area of steel AS is always going to be the moment divided by 0.87 FYZ. Okay, so that's something to take note of. So let's look at an example. Then maybe from there we'll see how all of these things work. Um, so let me put the example. So let's say I have um, so again a T section. Um, I have my AS in here. I have my neutral axis which lies below the flange. So okay. Well, this means that my stress block, so I have a portion of it in for the flange and another portion for the web. All right. So this is your FCF, and this is your FCW. Okay, this is our FCW. Then here, FST. Please, the FST is supposed to align with the rebar. I always end up not drawing it too well. Maybe I'll do these corrections as I go along. Because of the way the screen is acting, I'm careful in trying to delete stuff. Okay. Oh, so I think this one looks much, much better. All right. And then, so again, so I'm write a question now. So the section, or let me say the T-beam, since we are looking at the T-beam. Yeah, my erasing is not working anymore. So the T-beam shown is to resist an ultimate moment, design moment, right, of 180 kilonewton meter. So our Fy, all right, so we have all the parameters and that we need. Let's see how we can solve this example. So here first, let's find, so the solution would be, so with the solution, let's find MF, okay? So MF would be 0.45. FCU, BF, HF times D minus HF over 2. All right. So this becomes 0.45 times 30 for the FCU. Our BF is 400. Our HF is 100. Um, our D is 350. Then our HF over 2, which is, so it becomes 100 over 2. All right. So when you do all of these, our MF in terms of kilonewton meter will be 162 kilonewtons. Okay, meter. All right. So since our MF here, the MF is less than, so the MF is less than the M, which is the 180 kilonewton. So this is our M. Because MF is less than M, then it means that our stress block extends below the flange. All right. So here it means that stress block extends below the flange. That's what this means. All right. So if that is the case, we want to find AS. All right. So that's the plan, find AS. But then how do we find AS? We first need to find SW. We need to find SW, which is the depth of the web in compression. So to find SW, again, we have to rewrite the equations and then find SW from the equation set. All right, we know that the moment M is equal to FCF Z1 plus FCW Z2. And our moment is 180, right? Okay. So 180, we know that FCF Z1 is 160. 162, sorry, no, 160. So 162 plus FCW, right? So FCW is going to be 0.45 FCU, um, let me just write this one then, times BW times Z2. All right. Um, okay, let me just take this now where I write it in terms of Z2. Um, it's been an interesting um, so our Z2 would be I think we wrote it somewhere. What Z2 is D, so to bracket D minus HF minus SW over 2. Um, so I can multiply everything in this bracket times 10 exponents minus 6. And the reason is because I'm converting everything into kilonewtons and meters. So I know what my FCU is. FCU is 30. I know my BW. BW, I think it's 200 or so, if I remember. Yes, 200 millimeters. What we don't know from this set of equations is the SW. Right? So we have to rearrange and write the equation in terms of SW. That's the plan. So that means that 180 will be equal to 162 plus bracket open 0.45 times 30 times 200 times SW bracket open D is 350 minus 100 minus SW. Okay, so minus SW over 2 all times 10 exponent minus 6. All right. So with this, we should end up with so 180 will then be equal to 162 plus, if you have to expand, becomes 2700 S sub W into brackets. This is 250 minus SW over 2 times 10 exponents minus 6. So if you have to rearrange, so let's say rearrange. If you have to rearrange, it means that we end up with SW squared minus 500 SW plus 13.33 times 10 exponents, I think 3 equals 0. So if you have to solve the quadratic equation, which is what we have now, solve quadratic equation, it means that our SW here would be 28 millimeters. Okay. Which is fine because if you compare everything, you realize that that would give us the right answer. So let's say we know that x is usually what s over 0.9. So this will give us so s here is going to be what hf plus sw over 0.9. So this is going to be 100 plus 28 over 0.9. And this will give us an X value of 142 millimeters. Um, so here, since X Since x is, well, if you compare x to d over 2, which is going to be half of d over 2, I mean half of d is 350. So half of 350 would be 175. So since our x is less than d over 2, it means that no compression reinforcement required. Okay, so we don't need any reinforcement in the compression zone. These are just to reiterate the fact that usually when you have a T or an L section which has a larger compression zone, the concrete will be adequate enough to resist compression forces without adding any compression reinforcement. Okay. We just take note of that. Um, all right, so now let's find the okay. So going back to the summation of the axial forces. Uh, so again, we know that FST is equal to FCF plus FCW. All right. So here 0.87 um so 0.875 we're looking for times okay, let me put it's gonna take me some time to be able to clean this. Screen is frozen for a while. I'll just give it some time. So times AS times FY. Sorry, whole thing becoming a bit messy because of the screen issues. All right. Then we have 0.45 FCU BFHF plus 0.45 FCU BWHW. All right. Sorry, BWSW. Or the right HF. Sorry. BWSW. I'll correct these things later. Let me just move ahead. All right. Um, so this is 0.87 times 460 for FY. We don't know what AS is. That's the whole point of why we are doing what we are doing. Times 30 times 400 times 100, I think, yeah. Then plus again 0.45 times 30 times a BW of 200 and times an SW of 28. Right. So if we are to find AS, then AS here will be equal to 616 times 10 exponent 3 divided by 0.87 times 460. All right. So this then should give us 1540 millimeter squared. So this is the area of steel required. So let's say maybe we are using 25 bars. Okay. So the diameter of one bar is 25. Typically the area of one 25 bar will be equal to roughly around 500 millimeters squared. So if you want to know the number of rebars, then let's got the total area divided by the area of one. So that's how we compute it. No calculator around me. Um, so that should give us roughly about 5, I think. Yeah. So 1540 divided by 500 will give me, sorry, will give me 3.08. So here I can say that let's use 4 bars or 4 normal bars, right? So if that is the case, then it means that so I can say um, provide yeah, screen is just not responding to anything. Okay, so I think it's finally come. So provide for 25 M bars. All right. And then let's find the area of the bars provided. Since one is 500 and there are 4 of those, then the total area becomes 2000 millimeter squared. All right. So here in this zone is the area required. Okay. But the area required will give us 3.08 number of bars, which is not an ideal number to use, right? How do we get a 0.8? So here we have to use 4. So we are using 4 bars. And since the area of 1 bar is 500 millimeters squared, therefore 4 bars, the total area will be 2000 millimeters squared. Okay. So here you decide. So we decide on the diameter. All right. Yeah. So someone can use a different diameter. Maybe we can choose, let's say, a diameter of 20. All right. Which means that the area of that diameter, the cross-sectional area will be 300 millimeter squared. And if that is the case, then that the number of bars needed will be 1540 divided by 300. And this will give us a higher number of bars, right? So that's the catch over here. So then this gives us 5.133 bars. So approximately we can use 6 bars, 6 number of bars or 6 bars. I mean, doesn't mean anything. So what this means here is that since we are using 6 bars, then we have to provide 620 bars. Okay? And then the area provided will be 300 times 6, and that is 1800 millimeters squared. So you can see that for this particular case, depending on the size of rebar that we go in for, the area provided will change. All right. So let's take a note of that. I think this should bring us to uh, basic. I mean, this is not really the end of beams, right? In terms of how to design beams, but this is just like a breakdown of the beam design process to some extent. We will look at a few more. Um, like I mean, in proper, or should I say, in real situations where beams are simply supported or beams have continuous support, how then do we find um, the area of steel required, whether it's tension or it is for compression. Okay. So our next topic that we'll look at, we'll focus on shear. All right. All that we've been doing so far is to look at bending moments, okay, or moment. Okay. So far we've been looking at moments and then using that to determine the area of steel that we need, whether it is tension or compression. All right, whether it is a rectangular cross section or a flanged section. Basically, what we're looking for is the area of steel, which is a longitudinal bars, right? Whether those in tension or those in compression. Okay. So I'll end the video here and then we can continue on the next video explaining the shear process or the shear design process. Thank you.